So welcome everyone. So my name is Roman Prokofiev. I'm coming from Exascaling Lab, University of Fribourg, Switzerland, and today I'm going to present you our joint work on ontology-based coreference resolution. Okay, so what is coreference resolution? What is the task? So the task is essentially to identify groups or so-called clusters of co-recurring mentions. And let's take a look at the example on the slide. You can see here we have two mentions. It's Barack Obama and Xi Jinping, the US and Chinese president, and later in the text they are referred to using different other mentions. And the task is to identify correctly these other mentions and put them in the single clusters. And here they are, on the slide, they are color-coded. So why the coreference resolution is important? So it can help us in many things. So first of all, if we can identify mentions that are referring to the original entities, then we can get more context about these entities, which means we can identify more relations and we can identify more precisely the type of these entities since we have more context. And so we can then do it like populate the knowledge base with it and improve our knowledge base. So this is very important. So how this task is usually solved, the coreference resolution? Usually, traditionally, it's solved with an NLP, a multi-step approach. And it involves several steps. So the first step is usually some pre-processing, such as part-of-speech tagging to identify the pronouns and other part-of-speeches that can be co-recurrent expressions. Then it does also some more high-level parsing to identify noun phrases and verb phrases and to identify the entities themselves using named entity recognition. Then the approach proceeds to identification of recurrent expressions such as pronouns that can refer to the original entities, and furthermore to determine the anaphoricity of these co-recurrent expressions, like it should understand that it trains does not refer to anything and should correctly identify this, and the proceeds to generation of antecedent candidates for the co-recurrent expressions and tries to cluster them and put them basically in the group of the clusters. So unfortunately, there are certain limitations of this approach, of the purely syntactic approach. And you can see them directly in this example. So this approach is when the mentions in the text are referring to the original entities in some sort of a different form, in terms of words, or it can be some sort of ambiguous form or phrased a bit differently, then this approach is not able to identify. So for example, here it is not able to identify that Barack Obama is a US president and Xi Jinping is a Chinese president because they are formulated completely differently. And it doesn't have this knowledge. And we can try to fix it using our semantic knowledge, because we know that Barack Obama is the president of the United States and we have this in a knowledge base. And if we link this correctly, and if we identify the type of the noun phrase correctly, and if we link the entities, we can fix the clusters produced by the system. And that's what we do in our work. So we take the output of the existing coreference resolution system, and in our case we took the Stanford Coref. We take the clusters produced by this system and build our system on top of it. So you can see the clusters, the sample clusters here to illustrate the workflow of our system. So you can see that US President and Barack Obama are in two different clusters, and then we have a third cluster to illustrate another problem that if the words are like the proper nouns mixed together, so it puts the traditional NLP system can put these mentions together. So you can see here Australia and Quintet Australia put in the same cluster because the system thought these are the same engine. They both contain Australia and then Quintet, so it decided, well, that's the same entity. Well, actually one is the name of the country and the other is a company. Okay, so and what we propose is to take the output of this cluster do some pre-processing, the entity linking and entity typing of the mentions identified in those clusters, and then rearrange this cluster in two subsequent steps. First is we try to split the clusters if the mentions in the same cluster are different in terms of the entities linked or the types presented in those clusters. And then after we split the clusters, we try to merge the clusters if we think that the entities in different clusters are the same or there is a type belonging to the entity in different clusters. So let's see the boxes in detail. So we start with the entity linking of the mentions identified by SANAPHOR system. So for entity linking, we use simply a DBpedia inverted index. The inverted index built on DBpedia labels, which are unambiguous representations of entities. And we have also tried to do entity linking with other approaches, such as DBpedia Spotlight, but unfortunately, you can see also from the previous presentation on the tables, they don't have such a great precision in terms of linking entities. And precision is really important here, because if we don't have really good precision in entity linking here, then we can screw up the later phases of our approach and introduce even more errors when we split and merge clusters if we didn't link the entities good enough. So furthermore, we go beyond entity linking. We do semantic typing, and we do it also by means of inverted index. We build an inverted index of labels of the types, and for this we use the Yago ontology, which contains those types and their labels, and we try to match the mentions of entities with the labels of the types produced from our ontology. And we can see from this example here that the US president can be matched to a president type or US president type if there is one in the Yago ontology. Okay, after we have everything linked in our clusters, we proceed to the core steps of our pipeline, and we start with the cluster split technique. So you can see the cluster split proceeds as follows. If we have two different entities in the same cluster already linked, or if we have an entity and the type which does not belong to these to other entities or its antecedent types, so we check also the hierarchy, then we proceed to split these clusters. However, there are a few issues that needs to be solved before splitting the cluster. First of all, we have to do something with the mentions that were not linked, and there will be often such mentions. So for this, we have developed the following approach. If we have the non-identified mentions in the cluster, we first identify the exclusive words that belongs to the identified mentions in the cluster, and then we check the overlap of the existing words, and then assign the non-identified mentions to the clusters that have overlap with these existing words. And the second, to further improve the quality of the entity linking, we completely ignore the identified mentions which are complete subset of other identified mentions, such as when you have in the text something as Aspen Airways and Aspen, we're not sure. Maybe the entity linker will link Aspen correctly, the configuration to Aspen Airways, but maybe not. Maybe it will link it to a city or something else. So anyway, we just ignore this mention and do and link it to Aspen Airways, to the longest possible match. Okay, and after the cluster split, we proceed to cluster merges, and it works similarly to splitting. If we have entities like same entities in different cluster after the linking, or if we have a type that belongs to the entity or any of its antecedent types, then we merge the clusters. So we evaluated our approach on the standard FORNLL 2012 shared task on reference resolution, which also Stanford, all the reference resolution systems evaluate on. It contains over 1 million words, and as metrics we use precision recall and F1 for the case of clustering. And one additional thing is that we also evaluate separately the now-only clusters, which is important in our case, again, for the cluster split step, since we do not have any semantic knowledge attached to pronouns, and we do not reassign pronouns during the cluster split, and it may influence the performance of this step. So here are the cluster optimization results. So first of all, we can see that our system improves on top of Stanford graph in both split and merge tasks, which we evaluated separately. So it improves both in both tasks in terms of F1, and for exactly as we thought for the split task, the improvement is much greater in terms of when we have noun-only clusters. It's around 11%, while for all clusters we have only 3%. So this suggests us that we need to do something with reassigning the pronouns. This happens mostly because of pronouns. So noun-only clusters, the clusters that do not contain pronouns. And for the merge task, the improvement is good in both now all clusters and noun-only clusters, and ranging between 12 and 17%. So in conclusion, we can say that leveraging semantic information improves reference resolution on top of existing NLP systems, and second is that performance improves with the improvement of type and entity linking. So if we will have better recall in terms of entity linking, we can identify more entities and in the cluster and improve it even further. And also the complete evaluation code of our system is available online and GitHub, and this presentation is also available online as SlideShare, so you can always look up the slides later. So thank you for listening.
Question for the speaker? Yeah. Okay. Ask question. All right. Sorry, I don't see. You have a question? No. Go ahead. Go ahead.
Sorry for asking another question. Yeah, thanks. Great work. I was wondering if you had a chance to compare your work with Claudio Giuliano's work that also used knowledge base for co-reference resolution.
No, I guess we didn't compare. But if you have the reference, I would like to discuss.
Is there anybody from FBK in the room? From Italy? No?
Yeah,
Yes.
behind you.
Yes.
Maybe you can talk to these guys.
Okay, okay. Thanks.
Okay, any more questions? I just wanted to ask you something. Got a question?
Yeah.
Sorry, I cannot see you there with the column. Yeah.
So do you have any ideas how to kind of bring some more semantics into the pronoun part of the co-reference resolution?
So I have an idea, since we kind of use only the output of existing systems, and we use only the clusters, but we can, so it's not easy to kind of integrate ourselves on top of Stanford system, because we need to go into the code and kind of to plug into these existing systems. But I know there is a kind of a confidence score also assigned to pronouns, and also the pronouns are assigned to the previous mentions. And if you go deep into the kind of system, probably you can get these linkings to other linkings of pronouns to other mentions, and we can use this to reassign. But again, we didn't do this. We operated only on the output clusters themselves.
Yeah? Okay, I've got one question myself. Can I have a microphone?
So I was just wondering if, so since you're building your system on top of the Stanford clustering, right? If you have observed any cases in which your splitting and merging algorithms introduce some errors that were not there before?
Well, yes, it mostly again relates to the quality of entity and typing. So the process of clusters and the merge and split steps is quite straightforward, except for the few heuristics for splits. So it mostly depends on the quality of entity and type linking. And we can even further, we can even do type linking a bit differently, a bit what Andrew told during the keynote. So we can even extend it using this kind of approaches for type linking, and we get even more improvements with this.
Any more questions? Okay, so thanks a lot to the speaker.